All right, guys, so we're going to go ahead and continue today in chapter, which was the chemistry chapter, nail product chemistry. We left off specifically on page 118, 119. So, página 118, 119. All right, guys, so the reason I'm going live on here today is I'm starting a new thing to where for all my part-time students who do not come consecutively, so you guys can access these videos. Any old prior students, if you guys want to go ahead and use it for study purposes, you guys can also do that. So let's go ahead and get started. So page 118, 119. Yesterday, the last items that we talked about. So we were mentioning how long it takes for your dehydrator and your primer to resurface, or your oils to resurface back into the nail. We want to make sure that we understand that it does resurface back up. So if you are taking too long, we have to reapply both of these, cleanse and prime. Overfiled or damaged nails, we mentioned that the nail is now a bit more porous, therefore in this case we might have more lifting problems, right, where the product might seep more in there. One of the signs we mentioned was the nail feeling bruised, almost like bruised, not painfully but bruised, right? And we mentioned that this can happen from the trauma from the overfiling, or it can happen from the porousness of the liquids kind of interbedding into the layers of the nails and into the nail bed, right? So we mentioned that if the client is too damaged, or they're ripping off nails, or they have all that damage, we are going to maybe refuse service, or alternately, we are going to recommend maybe a manicure, a hot oil manicure, maybe a paraffin treatment, something in that sort. We mentioned that, of course, because whether it's damaged or not, regular non-damaged natural nails are considered still porous. So in that sense, whenever we touch water, acetone, we have to remind our clients, even the gel remover we used yesterday, that's acetone-based product, making sure that they know that the nails will feel softer. So being more careful. It is not that we damage them, it is that they absorb some type of liquid. Where we specifically left off was the figure 5-6 on page 121. So we were referring to image A. So image A here on page 121 is showing that we see excessive peeling, multiple layers of the nail. This basically shows how the nail cells are pulled away when we basically pry a residual coating, right? So when it's residual coating, that's referring to it could be acrylic, it could be a gel, which is why it could even be a jelly base or a rubber base, which sometimes again are they are advertised as safe to rip off, right? So as we could see, don't rip anything off. The goal is to come in and do that final layer of soaking so that it is safe and it does not cause this damage. So microscopically, moving over to image B and C, both B and C are showing damage caused by using a wooden implement. So the orange wood stick, which normally we pull out and use on diabetic clients or more sensitive clients in that sense. So we would think that this wooden pusher is more safer, but it really can still cause damage, especially again with when the nail is soft. Right, so we are running that risk. So as we could see in figure B and C, we can see some scraping, right, which is why I try to refrain from scraping when we do removals as well. And then image D will be showing, this one is magnified 150 times just to show the residual product left on the nail. So if sometimes we have a little bit of base gel, maybe acrylic or polygel, that's how it will show. It is showing the filing streaks. So, making sure we are being careful and not using an aggressive file on our natural nail, so we don't cause damage. All right, so everybody basically understands what grit we should be using for the natural nail pressure. So we're going to go ahead and keep moving. So page 121 at the very bottom. So now we're going to talk about, it mentions compare nail coating products in terms of their chemical and their physical reaction. So In the other chemistry chapter, we do talk about the difference of a chemical reaction or a physical reaction. So some of the things we've mentioned here was that the chemical reaction, as we've mentioned, happens normally in many instances. In order to create a chemical reaction, you most likely need to add one chemical to another chemical to be able to create a new chemical. When we are dealing with a physical reaction, this is basically referring normally to evaporation, where we are dealing with, for example, a regular polish. The regular polish will evaporate. So without adding anything to the regular polish, it becomes a hardened film, right? So understanding the difference between both. But first we're going to start with the term coatings. So when we refer to the term coatings, it's referring to products that cover the nail plate with a hardened film. So when we turn the page to 122, it gives us exactly those two that we've just mentioned. It says, when we break down the two categories of coatings, again, we categorize them by either a chemical reaction or a physical reaction. So the first bullet point shows coatings that cure or polymerize will normally happen by a chemical reaction. When we deal with curing, we are referring to anything that goes in the lamp. Anything that goes in the lamp, as it is exposed to the photoinitiator or to the UV light, right? It becomes a new substance. So therefore, this happens due to a chemical reaction. And then polymerization, whenever we are dealing with acrylic, this also happens through a chemical reaction, right? In order for both of these to happen, it has to happen through a chemical reaction. And then we have bullet point number 2, where it talks about coatings that harden upon evaporation due to a physical reaction. So again, we don't have to add anything to that substance for it to become that hard coating, right? So that is the difference between both, understanding for testing purposes what is definition of coating and the two categories of coatings. All right, so everybody understands that, right? Later, like I said, we will go into detail as far as more examples and more description as far as a chemical reaction versus a physical reaction, but in conjunction for testing purposes, we want to remember those two coatings and those two categories. All right, so now we're going to go ahead and get into page 122 in the nails book. Understandings, the basics of monomers and polymers. Okay, so let's get into it. Monomers and polymers. What is it? Why is it called that? What do we use it for? The breakdown molecularly, all of that, right? So we want to really understand what is a monomer and what is a polymer. So starting, follow along. I'm going to go ahead and I'm going to read a little bit here. It says creating a nail enhancement is a good example of a chemical reaction, right? As we've mentioned, it says trillions of molecules must react to just make one sculptured nail. Write that down, jot it down, take a picture memory. That will be on your exam, that basic sentence as far as how many molecules will we find per nail enhancement or per one nail? Trillions. So highlight it, write it down, okay? They'll give you billions, trillions, all the illions, but it is trillions. There are trillion molecules per nail enhancement. Right, so trillion molecules per sculptured nail. And so moving on, it says durable and long-lasting coatings and nail enhancements have been created by these chemical reactions. Okay, so let's go ahead and let's start with the root word of monomer and polymer. When we are dealing with the term monomer, monomer has a root word known as mono. Mono is referring to one. Normally it will refer to one depending on what we're referring to. It could be, for example, if we're referring to religion, it will be monotheism. If we're referring to monogamy, right? So anytime we see the word mono, we'll be referring to one unit. So I'm just going to put one. So now that we kind of understand, we're going to go ahead and read from the book here. It says the molecules in the product join together in an extremely long chain. The chain that they're referring to we see in figure 5-7, where it kind of looks like one straight line, kind of little, like little cylinder blocks, and they are attached by little green, I guess, lines you would call it, right? So what exactly is that referring to? It says that these gigantic chains of molecules are called polymers. Polymers can be liquids, but they are usually solids. It says the chemical reaction that makes polymers is polymerization. So due to the fact that when we think of polymers, for example, it says, what are some examples of polymers? Because we think polymers, we immediately think acrylic powder, right? Plastic. It's saying Teflon, nylon, hair, wood. These are all polymers. Protein polymers. So it's saying that nail plates are made out of proteins, including keratin. So nail plates and hair are also made out of proteins. So when we think of these polymers, right, and I'm going to go ahead and I'm going to draw that molecular chain here. When we think of acrylic has long molecular chains. When we think of gel has short molecular chains, but we'll get there, right? So basically looking at the molecules and how they're all kind of combining and attaching when this nail is polymerizing, when we think of these, because these are one unit, right? These are going to be the monomer molecules. And then these are going to be the polymer molecules. And so again, the moment we come with our acrylic brush to dip it in the monomer and put it in the polymer, it creates that chemical reaction. And I'm going to explain another example of polymerization right now, but let me translate first, right? So in this case, molecularly wise, we have our polymers and our monomers. All right, so we understand monomers, we understand polymers. Now we're going to go ahead and we are going to talk about the physical polymerization and how that works. So first, let me write that down. Polymerization, right? Polimerización. All right, so the process for acrylic, polymerization. I want you guys to think of all of these little molecules like if they were to be in a baton race. What is a baton race? If you guys don't know, a baton race normally is basically there's a track. It's like running, right? There's the start of the race, and then we have different areas. In these different areas, you have people from the same team standing there. Polymerization is like a baton race, right? We have the beginner here, the one who's going to have the baton. It's like a little thing that they hold. They run all across the race, and as they get to the different parts, they hand the baton over to their team member, right? So polymerization is basically very much like this. The race starts. When does the race start on the enhancement? The moment you dip that brush into the powder, the race starts. The first person or the first molecule will then receive that energy that's created from that chemical reaction, and what it does is it grabs it, it takes it, and then immediately it releases it to the next molecule or the next baton player, right? So this molecule does the same thing. They receive that energy from that chemical reaction, and then boom, they send it off to the next molecule, so on and so forth. By the time that the race ends, or by the time that the nail polymerizes completely, about 3 to 4 minutes hypothetically, but normally it takes the nail about 24 hours to fully polymerize that process, right? So when we think of polymerization, I want you guys to think of it as these molecules grabbing this energy created by that chemical reaction, immediately getting rid of it, and so on and so forth to create that full nail enhancement. The issue with that bad chemical reaction, right? As I mentioned, this chemical reaction has to happen. So why does it burn? Why does it sizzle sometimes? Because what happens in this case is improper ratios. For example, we put too much liquid or